All right. Okay, this new chapter is it's going to be different than what we've been doing. We've been kind of leading up to the same thing. You know, we've been pursuing stoichiometry for the last 9 chapters. All right, we finally got there. Stoichiometry used a little bit of everything. All right, used stuff from almost every chapter. If you look at some of those problems you had, like that, you guys, some people were still doing back there. Make it up the test. Anybody else need to make up the test, by the way? If you look at some of those problems, you'll notice there's stuff from every single chapter we did. You had to be able to use the periodic table. You had to be able to talk about writing the compounds correctly, the charges correctly, octet rule. And that was just to write the formulas. Then you had to put the formulas together and make equations, the equations, balance them. Then you had to do the conversions of grams, the moles, moles to atoms, moles to molecules. You even had a density problem thrown in there, so that was fun too. All right? All right, Maddie? All right, so we are not going to do that from now on. Every chapter up until, for the last 9, built on itself. The next few are going to basically be hit and miss. We're going to spend a couple of chapters on gases. I want to talk about gases here, show you this little animation here. It's kind of cool. And that'll get us started. Then we're going to talk about solids and liquids. Then we're going to talk about solutions, put them together, and we'll have acids and bases, and then finally nuclear. So we have a lot to do, but they're not going to be like it has been. Half the year, wholly half the year was building to that one thing, stoichiometry. All right, now let's talk about gases. Now I'm going to show you this little animation. You guys have all used apps like this on your phone that all use real physics, basically, I call it. You know, like when I'm going to put some molecules into this container, and they're going to act the way gas molecules would act. And you pretty much, you use things like this on your apps, basically can do this. It's pretty amazing. They're pretty incredible programs. We take them for granted now. You can have your little skateboard guy, and you can little cars you're driving, and they all follow the rules of physics. All right, it's pretty incredible that we can do that. But it makes it easier for me to explain gases and the kinetic theory when I use these. All right, now look what happens. That's what's going on. You watch those little molecules going around in there. That's what's happening. That's what a gas really would look like if you were to be able to see the molecules of the atoms. They're all moving around randomly, and they're not really being attracted to each other. Basically, they're filling up the entire space. Watch what happens if I make the size of this guy bigger. Okay? The gases just fill it up. What would happen if I increase the temperature of this guy? Let me make him a little smaller now. What if I increase the temperature of this guy? Put a little heat underneath him. Let's watch what happens then. What do you think is going to happen? They're going to move faster. Look what's happening to the temperature. Obviously, it's going up. They're moving faster. Okay? If I don't make the size of the container any bigger, you notice what's happening to the pressure gauge here? Can you see that? Okay? That's it's going up even higher and higher and higher. And if I'm not careful, and by the way, you watch these guys moving around, all right? If I heat it up too much, maybe I'll make it a little smaller. What's going to happen? Let's see. Keep heating it. Yeah, it's going to blow it up. And then it all escapes there. Okay. Well, basically, that's what's going on. Let me reset this. That's what's going on when you have a gas. And let's watch what happens if I have smaller particles. Okay, they're going to move around really fast. They're harder to see on my computer, my screen there. So. And actually, that's going to be a little off. There we go. Okay, so everybody can see. I have to tape this one because I'm going to add something new to the end of it. But basically, what you're seeing here is an example, or is an illustration of what I would call, or what we call the kinetic theory. These molecules moving around, hitting each other, all right, randomly moving, and I could change the temperature, volume, and pressure of them, and it changes things about them. That's basically the kinetic theory in a nutshell. Now, I want you to keep this thought in mind as I give you the actual statements of the kinetic theory in your notes, okay? And I'm going to refer back to this every time I start a class, from pretty much from today on for the next couple of days, next week. I'm going to be starting with this to talk about the effect of temperature, pressure, volume, and all these different things, okay? Let me get rid of this right now. Now, so in your notes, we're going to talk about the kinetic theory and how it explains the properties of gases, all right? So, and that's what this whole chapter is about. This whole chapter is about the physical characteristics of gases. We're not going to really be using chemistry much in this chapter. Physical properties we're going to be talking about, not chemical properties. No periodic table, no writing compounds and formulas for the most part, no stoichiometry for the most part. There are going to be problems, lots of them, but they're going to be concerning the properties of the gases. And they're all going to be related to the kinetic theory. That's the basis of all of this. I've got to explain the kinetic theory to you very well today. Keep in mind my last little animation there. All right, let's start with the first statement. The first statement is actually the first statement of under atomic theory. All those little circles, all those little balls moving around in there, little ping pong balls, what do they represent? Molecules. Molecules or atoms. And we know that the very first statement of kinetic theory is going to be that all matter consists of atoms or molecules, very small particles. That's number one. It's not something new. It's something we probably remember from Dalton's law. Dalton's law of the atomic theory. Dalton's atomic theory. You saw it there before. Dalton wasn't the first one to come up with that idea. Remember, it goes all the way back to Democritus. We're talking about the Greeks long time ago. Everything's made of very small particles. That's the first statement. As you can see, as you just saw, those particles are in constant motion. Now, they're not in the same kind of motion in every single phase. The kind of motion you saw there a minute ago was a special kind. All right, it's describing an ideal gas law. There's no forces of attraction or repulsion. These guys aren't slowing down and they're not speeding up unless I do something to them. But even in a liquid or a solid, those particles are moving. Even in a liquid or a solid. And I'll explain that as we go on. All right, and finally, as you saw, if I change the temperature, I increase the kinetic energy of those particles. They move faster. Okay? I give them more energy if I increase the temperature or decrease the temperature. I give them less energy. Take energy away. All right, so there you have it. Those are the three things. That's not all. There are 5 statements, but those 3 apply to everything. Solids, liquids, and gases. Gases, however, have a couple of more things I'm going to say about them. Unique to them. The first one is, if you watch those particles hitting off of each other a few minutes ago, you'll notice that they never stuck together, they never slowed down, they just kept going. Every now and then they hit the certain ways, one would go off a little faster than the other one, but the overall energy stayed pretty much the same. They underwent what's called the elastic collisions. They don't lose energy in the process. Okay? And that's not the case for, in real life. Like, you do a lot of physics problems where you assume elastic collisions to get your answer, right? Have you talked about that in physics? Right? You talk about, you're shooting a pool, you have billiard balls on a billiard table, and you're shooting. And you can calculate pretty accurately, even though these are not by any means elastic collisions, you can calculate pretty accurately, knowing the momentum, knowing the mass and the velocity of one cue ball. You can tell if it hits at this angle where that ball is going to go. It's all physics. Well, the fact is, it's not really an elastic collision. Even if I don't have a pool table, even if I have, and you've seen Schrader use, I'm sure, those air hockey kind of tables. So they have air, you use those, yeah. Well, there's a lot less friction there. Even those, if I push them along there back and forth, they're eventually going to slow down and they're going to stop because there's some friction just from going through the air. When they hit, you hear a sound. They get a little warmer. They give off a little bit of sound energy as well. They're losing energy all the time, and that's why when I shoot pool, that ball's not going to keep going around the pool table forever. You can't bank it off the pool table 17 times. It's going to stop by then. All right? But in gases, they do. They are pretty much elastic collisions. As long as the temperature is high enough and the pressure is low enough, those molecules are far enough apart, and they're going to pretty much act like elastic collisions. They're not going to lose energy. And they're not going to be attracted to each other nor repelled from each other. This 4 and 5 here only apply to gases. They do not apply to solids and liquids. There's clearly solids and liquids being held together. They have, attractive forces holding these guys together. Otherwise, we wouldn't be able to measure their volumes and stuff. All right. So that's the kinetic theory as it applies to gases. Now, it's my job, and I have several demonstrations here for you today. It's my job to relate this kinetic theory to specifically why gases have these properties that we're going to see. Properties that you're all familiar with, by the way. Got some stuff in the fume hood, and got some more stuff we're going to do over here. All right? And you're going to hopefully get a chance to see all this stuff and explain it to you. So let's talk about how this theory is applied and is responsible for the properties of gases. And we'll start with the two things that you all have probably learned in elementary school, maybe even. Not just middle school, but elementary school. Has to do with gases and liquids or solids, shape or volume. Look at it. This solid, this thermos itself is a solid. Doesn't matter. This guy is going to have the same shape and the same volume no matter what I do to it. But the water that's in here, if I pour it into here, will it still be the same volume, pouring this into here? Yeah, but will it have the same shape? No. So a solid has a definite shape and a definite volume. A liquid, I can measure the volume. It's a definite volume. It doesn't change, but the shape changes. What can I say about a gas? What does he have? He has neither, right? He has neither a definite shape nor a definite volume. No definite shape, no definite volume. He basically expands to fill the container. You saw me do that when I pulled back and made that container bigger a minute ago. All the molecules just kept moving. They filled up the whole space. Okay? And that's why the property is called expansion. It has no definite shape, no definite volume to a gas. If I open up a bottle of perfume in the front of the room, you'll smell it in the back of the room. It's going to try to fill up, as it turns into a gas, it's going to try to fill up the entire room. Okay? So that's expansion. Next one. One we don't, this is the word that you often apply to liquids. Gases are fluids too, and I wanted to illustrate that for you with a little demo. Okay, it's a neat little demo. I've done this for a long time. It's kind of cool. Copy that definition down, and I'll explain to you what we're going to do. Took a little candle, and I put him into this beaker. Okay? Y'all see that candle in the beaker? All right. Now, I'm going to take some baking soda. I'll put some into another beaker. And I'm going to take some vinegar. And I'm going to add the two together. I think everybody knows what happens when baking soda and vinegar meet. We've seen this before, even again as a kid, probably for your little volcanoes when you made them. What's being produced here? Carbon dioxide gas, right? All right, now I've got a beaker of carbon dioxide gas right now. Can't see it, but it's there. This is not magic, but watch what happens. I can pour it like any other fluid, and I can put out the candle. Isn't that cool? Yep. You couldn't see it, but CO2 is heavier than air, so it went down to the bottom, and it smothered the candle. That's what's in here. CO2 is in here. By the way, don't tell Al Gore we're making CO2, carbon dioxide. Al Gore? A little warming. Right, there you go. Okay, so yeah, we're ruining the environment right now. But for a reason. Hey, no better, sacrifice of some CO2 molecules than to teach you that gases are fluids also. The particles slide past each other, and I'm able to pour gas. That guy's more dense, so we can't see it, but he actually does that. Gases also, there's a lot of things about gas that a lot of people don't get wrong on this. Is gas a matter? Yes, gas is matter. It has mass. All right, there are masses to gases. It's pretty bad, but yeah. So basically, I just wanted to show you that nice little demo for that one for the fluidity. But they also have a very low density. Gases, compared to their liquid phase, are much less dense. 1,000 times less dense than their solid or liquid phase. Someone's just driving a truck down the hall, I suppose. Great. Okay. Good drilling. So, if I have just a small, tiny little bit of water, for example, an eyedropper full of water, an eyedropper would have maybe about half of an eyedropper be about a milliliter of water. This is a tiny eyedropper. It would, if I were to totally vaporize it, fill up this entire beaker. Okay, it's going to be 1,000 times greater volume, and therefore 1,000 times less dense than the liquid that it came from. Solids and liquids are pretty much the same. They don't really change much in density. I mean, although there are some weird guys like water, who is in a solid phase actually less dense than the liquid phase. Most solids are more dense than a liquid phase. But all gases are much less dense than the solid or liquid phase. By a lot, by 1,000 times. Okay. Another thing about gases, and this next one explains why I'm going to have 2 chapters to talk about gases. Compressibility. This is the only reason why we have to spend 2 chapters on gases. If it weren't for the fact that gases were compressible, I wouldn't have to do this. I wouldn't have to spend this much time. You realize that we are going to have only 1 chapter to cover all of solids and liquids combined. We're going to spend 2 full chapters on just gases. Why would that be? Let me show you. I can read the volume of this vinegar that's in here now, and it's 200 degrees. It's 200 milliliters. If I were to change the temperature in this room to 100 degrees, all right, Fahrenheit, or cool it down to 30 degrees Fahrenheit, all right, or I could change the temperature, I could change the pressure in this room. Guess how much water I'll still have? 200 milliliters. That is not the case for gases. If I change the temperature, if I change the pressure in the room, if I take this thing, this syringe with a cap on it, to the top of a mountain, or to the bottom of the sea, it's going to have a different volume. It is useless to read the volume of this, which is about 80 milliliters. That 80 milliliters will completely change depending on the temperature and depending on the pressure. So if I push down on this and I double the pressure, what happens to the volume? It decreased by, guess what, how much? No, decreased by half, right? Okay, so double the pressure, half the volume. All right, we're going to actually do a little lab on that too. It's called Boyle's Law. We're going to talk about the effect of pressure and volume and temperature all on gases. And there are going to be 3 laws that we're going to talk about. And that's why this whole chapter is here. If it weren't for the fact that I can compress these guys, I wouldn't have to spend this much time on it. Because I never cared what the pressure in the room. I will care now about what the pressure is in the room when we're doing a lab. We have a way to measure the barometric pressure. There's at the top of the roof. There's a weather station. So Mr. Schrader gets the reading of the barometric pressure every day. So we know the temperature of the room, we know the pressure in the room. That will give me an accurate volume of my gas, only by using those. So we're going to spend a lot of our time doing that. Okay? Now, the last one, this is one that I bet you can come up with the definition yourself, I bet. The fact that those gases, well, here, instead I'll give you the definition. You tell me what it is. You remember it from biology. The fact that that gas, when I made the container bigger, it just spread into that other area. What do we call that? When gases just spread out into a different area, go from high to low concentration by themselves, spontaneously. From biology, you thought, when it talked about osmosis. What's the word? You should know it. What's that? Diffusion? Yes, diffusion. Diffusion. It's a spontaneous movement of particles from a region of high to low concentration. And I'm going to illustrate this. This is the best demo here. These other ones are kind of little. This one's the biggest one. To illustrate diffusion and also do a calculation with it. Okay? Copy that down and I'll show you. Okay, particles move all by themselves for gas from high to low concentration. Doesn't take any energy to do it, just automatically do it. I'm going to illustrate this and also illustrate something about it that we're going to calculate. Okay, I'm going to take some hydrochloric acid and ammonia, and I'm going to put them on 2 cotton balls. And I'm going to put them in a glass tube. You're going to see this in a second. If I were to open either of these, you've never used hydrochloric acid like this. This is concentrated hydrochloric acid. This is what I mix up to make your dilute hydrochloric acid. You would know it if you used this, because if you opened it, you'd have a choking fumes given off. I only mixed it up in the fume hood. Ammonia, same thing. Very, very nasty smelling. Ammonia. This is not the ammonia you have in your household cleaner like Windex. That's about 3 to 5% ammonia. This is 58% ammonia. All right, this is nasty stuff. That smells bad enough. Now, off camera here, I'm going to grab my 2 cotton balls. Okay? Oh, I can't remember which is which now. Wait, I better just. Well, I know. I can test it. That's a good idea. Let's check it out. Let's see. I'll put it next to here. Oh yeah, that's right. See that smoke coming out of there? All right, in the fume hood. That's why I'm doing it in the fume hood. I know which one that is, because it won't do it to this one I'll mention. Nope. So that guy is the ammonia. And this guy must be the hydrochloric acid. Those 2 guys get together. That's the kind of cloud of you're going to see. Okay? All right, so let's bring these guys over here. This is my little glass tube. I'm going to put the cotton balls soaked in each of those things in here. And let me make this so everybody can see it. All right, this will be the HCl side. This will be the ammonia side. Okay? Did I put them right? Which one was which? Which one? You think this is the ammonia?
That's the acid.
No, that's the acid. Okay. All right. That's the cloud I will get. All right. This is the acid because it wouldn't react with the ammonia otherwise. Okay. All right. So acid on what side over there? It's on the right hand side. Okay. I don't want to mix them up when I take them over here. Now I'm going to put them in at the same time, and I want you to watch what happens as they sit there. Okay. Oh, can you open that window over there and open that door? Open that door. Door.
How do you open it?
Just however you would open a window. I think you can figure that out.
Just pull it up and push it up. Yeah.
Okay. Keep your eyes on that. All right. And we're going to look inside of this one. We're going to see where those 2 things. Right now, they're diffusing. The HCl is moving this way. The ammonia is moving that way. And when they meet, you saw that little cloud I showed you in the fume hood. They're going to form a cloud of ammonium chloride. All right. Now, hopefully you can see this here. This is the HCl side, right? Did I put it on the right side? Yep, and that's the ammonia side. Watch. Eventually, they're going to meet. Ah, there it is. I think I see it. No. No, not yet. It's coming. It's coming. I'm standing here in front because you actually see better with the camera, with my shirt, rather than like that, I think. Okay, it worked faster in the other class. You know why? It was fresh. I just dumped it right in there. They've been sitting there all afternoon, but hopefully it'll work. I can see it now, right there. Can you see the cloud?
No.
Can you see the cloud? Right there. That's worse. Can you see it with a white background? No, you can't see it with a white background. You see the cloud forming here? You will. People in front have to be able to see it. Yeah, you can see it a little bit. It'll get a little stronger there in a minute. Can you see it? Now, look.
A little bit, yeah.
What's something darker black? Here. This is really black. Can you see it now?
Yeah.
There you go. All right, this cloud's forming here. It was a little bit darker, a little bit denser in the other class. There's something I want you to notice about the cloud. It formed on which side? The HCl side. That means something, and I'm going to explain something to you about what that means in a second. But hold on. Let me get rid of this stuff. You can see it now. No, you can't close the window. I'm going to get rid of this, It's stuff is nasty stuff. You don't really want to be breathing it. That's why I open it up in the fume hood. Okay? Wait. It's hot, so I'll get a little smoke there. It's like my mom. Alright. Don't do drugs. Especially these drugs, because how you're going to do this stuff. But anyway, yeah. I want to talk. Oh, I guess I could use that back. Yeah. No, I can just draw it. What happened here? What happened? Let's take a look. You can close that window now that it's out of here. All right. Let me show you. Here was my glass rod, my glass tube. Okay? This side was HCl, and this side was the NH3. Is that how I had it, right? Was that way? Okay. The cloud formed on this side, right around here. Why? It's a very simple reason. Well, first of all, let me ask this question. Let me answer this question first. Which one must have been moving faster in order for the cloud to form here? It's amazing. I'm getting two answers out there. Which one, if they both were put in at the same time, which one must have been moving faster? This guy, right? Not HCl. He covered more ground in the same amount of time, and they met there, correct? So this guy moved faster than that guy. Why? It's a very simple answer. Nope. Something easier than that. Say I were to have a race with Mr. Norse. Who would you put the money on? Me. What's a good reason for that? Smaller. Well, lighter, right? Basically, how much does NH3 weigh? N is 14 about, and H is about 1. So 3 times 1 is 17 total for grams per mole. How about HCl? What does he weigh? Cl is 35.5, and H is 1, so that's 36.5. He weighs more. So that's why this guy moves faster. And I can tell exactly how much faster by a calculation, by a law called Graham's law. Okay? Graham's law says the rate of diffusion is inversely proportional to the square root of the molar mass. Now, that sounds complicated, but it's not. It's not really that bad. We'll be able to do 2 quick problems in here, and then we'll be done. Okay? And this makes complete sense, you would think. You know, it's going to be inversely proportional to the masses because as the masses get bigger, the guy's going to be diffusing slower, right? Or more slowly as the guy gets bigger. That just makes sense. Heavier, I should say. Here's what the equation looks like. Write it down. Rate 1 over rate 2 is going to equal the square root of the molar mass of 2 over the molar mass of 1. That's why it's inversely proportional. And by the way, this is the best square root form I could get, symbol I can give, but you know what the square root, right? Like that. All right. Now let's try using this equation to actually solve 2 quick problems. It's not that hard. I think most of you will be able to do these in the time we have remaining here. Copy that guy down. All right. So, first of all, you can all answer the first part of this question, can't you? If equal amounts of helium and argon are placed in the container, which one's going to get out of there faster? What's the obvious answer? Helium, he's lighter. Okay. But I've got to solve, if it wants to know how much faster, okay, I have to solve the equation. So I'll solve the equation the way I've always solved equations. Anytime I've got an equation, I told you what I want you to do. Write down the given information to the side, write down the equation, rearrange it, and solve for it. That's what we're going to do here. So we'll have, I'm going to abbreviate here, rate 1, rate 2, molar mass 1, and molar mass 2. Okay? Now, we don't know either rate 1 or rate 2. All we care about is the fraction that they're going to be. You know, for example, if they're going to be half as fast, or twice as fast, or 3 times as fast. I don't really care what the actual absolute value of the rate is. It's only a comparison. What is the molar mass of 1? What's the molar mass of the helium? 4.003 grams per mole. And what is the molar mass of argon? 39.948 grams per mole. Okay? There's your given information picked out. You say, well, why do I have 2 variables again? I don't really care because all I'm going to want is the fraction. R1 over R2. Rate 1 over rate 2 is going to equal molar mass 2 over molar mass 1. Okay? So it's going to equal 39 point, and square root of that, by the way. 39.498, 948 over 4.003 square root. Can you do that on your calculator? And I left out the units. Why did I leave out? Why do I even care what the units are? What are they going to do anyway? They're going to cancel. I was looking for the ratio. That's all I care about. So divide 39.948 by 4.003. What do you guys get? And take the square root of it. I hope you all know. The reason I'm having you do this one is just make sure you can do square roots on your calculators. Everybody's calculator is different. Maybe you haven't used it in a while. Did you all get 3.16?
Yes.
Correct. 3.16 times as fast. Okay, that's how many times as fast. 3.16 isn't an actual number. It's just that's how much faster it's going to go. 3 times faster. Okay, you understand? Make sense? All right. Let's just do one more. I'll ask it a different way. You guys probably figure out I'm going to ask the other side of the equation this time. I'm going to give you the rates, and I'll ask you the molar mass. Makes for a little bit more work, but not too much more. Basically, if I know the rates, you know, the ratio of the rates, and I know the molar mass of one of the guys, I can figure out the molar mass of the other guy. And that's what I'm going to do here. So, rate 1, rate 2, molar mass 1, molar mass 2. There are 2 reasons I want to do this example. Actually, 3. One, I'm doing it a different way. I'm not solving for the same variable. But the other 2 reasons are this. Reminding you of molar masses. What do we have to do with diatomic elements? Let's not forget, hydrogen is diatomic. I'll have to multiply that guy by 2. And lastly, the math at the end is a little different because you're actually underneath the radical sign. So we'll talk about what happens there. So let's plug this guy in. What we know. Do we know the rate of 1? Well, it's 1/20th as fast as hydrogen gas. So 1 and then 20, right? Those are your 2 rates. 20 times as fast. Okay? Who's the guy that's 20 times faster? Okay? And where am I going to put the molar mass of hydrogen? That's my question. Think about it. Where's the molar mass of hydrogen going to go here? If I'm assuming the rate of this guy is 1, and the rate of this guy is 20, all right, this is only 1/20th as fast. The unknown, the guy we're looking for, is only 1/20th as fast as hydrogen. What does that must mean? It must mean hydrogen is down here, which is going to be 2.0158. Where did I get that from? I simply multiply 1.0079 on the periodic table, right, times 2, because there's 2 hydrogens. And this guy is your unknown. He's your unknown. We'll make him X. So here's my equation. R1 over R2 equals molar mass 2 over molar mass 1. What's R1 over R2? It's going to be basically 1/20th, all right, equals, let's plug our numbers in, M square root, by the way, square root of. M2 is 2.0158, square root of, over basically X. Right? Let's do 1 over 20. What's 1 over 20 on a calculator? 0.05 equals 0.05 equals the square root of 2.0158 over X. How can I solve that? I told you the last thing I want to do is talk about how to do the math for this. What could you do to solve this?
Right.
Square both sides. Exactly. What's the square of 0.05? Correct. And the square of the square root of this guy is going to be 2.0158 over X. Everybody see where that came from? That makes sense to everybody mathematically? If I square the square root of this guy, it comes that guy, right? Make sense? Good. All right, so now I just cross multiply, and I get 0.0025x equals 2.0158. What is X? Divide that by that. What do you get? It's a pretty big number. Anyone? 806, is that correct? All right, it's a pretty big number. You have to have an atomic mass. So, well, no element has an atomic mass of 806. Is that a problem? No, it actually isn't. Here's why. 806 grams per mole is of the compound. It could be a molecule. What if the molecule is like, C4H something, N something, and you have to add all those up, right? Couldn't that possibly be 800? Yes, although that is awfully heavy. But that's how you do it. That's the exact same way you do it. Okay? All right, good enough. Your homework, well, you don't have any homework. It's Friday.